Hi, this is Calvin Cox. It's a Thursday evening, 8:23 p.m. It's March 28th, 2013. The talk I'm going to give this evening is about hot and cold, weather patterns, and hopefully it'll wind up with a good suggestion about what mankind can do to offset the heat gain we appear to be currently receiving on planet Earth. This is I don't know how this talk is going to turn out. I haven't had adequate time to really prepare it well, so I'm just going to try and go through it. Hopefully it'll work out all right. What you have here is warm water, and what you have here is ice. And I just wanted to get an ice cube, but it didn't have one in the freezer, so I just got the bottle of ice. Now, this would be like the North Pole or Antarctica, and the warm water would be like, the Indian Ocean, Pacific, near the equator, whatever. They both, even though they're thousands of miles apart, I'm using this as a representation, they both affect each other. Okay, the hot water is cooled by the cold, and the cold is warmed by the hot. There's interaction. There's air movement. There's the warm water here doesn't stay stationary, and the cold doesn't stay stationary. Water flows around the poles, and there's heat interchange. So you can see, and you hold them close. If you've ever put ice in a warm drink or a warm soda pop, you notice how it melts pretty quick. There's interaction. That's what occurs on the Earth. So you can understand that it's necessary for the seasons to come back in line. It's necessary that there be sufficient ice cover on the North Pole. Most of humanity, if you look on a picture of the globe and the equator, most landmass is north, is on the northern part of the Earth, above the equator. Most of it is. You just got to sit there and look at them, and you go, yeah, most of it is. You have South America poking down, and then you have Africa poking down, and the countries around the equator. But if you look at the totality of it, you'll see a majority of it's in the North Pole. That's why we're affected so much weather-wise, is because the North Pole has massive ice shrinkage going on. On Google, I typed in satellite. In the query section, I typed in satellite view directly atop the North Pole. And then on the fourth section down, had in there NASA first time releases picture from the satellite. It said like blue marble in there, so I clicked on that one. And then you can't see this real well, and it didn't have a color printer, but as you look at this, you get a real sense of what I was talking about with the warm water and the ice, how they're affecting each other. Up here being the North Pole clouds and ice, and here you see sand color. This is Sahara Desert. The United States is over here. England's here. Europe's right here. The sand coming across the Sahara. You have the Sinai in here, Egypt. And then comes on in deserts also all the way up over here. You have deserts in China, and they cover a large portion of the world. If you get a good satellite map, you can see the desert regions, the green regions, and the polar regions. You definitely get an idea of how much they could interact, and why it's important to keep temperatures lower on planet Earth, you've got to keep that North Pole area healthy and bolstered and replenishing itself with fresh snowfall, so it creates a sufficient pack. What's happening now? The ice is shrinking. Anyway, that's the major issue, and how that relates into everything is right here. We'll have this as real cold would be ice age, okay, and real hot would be like super hot, where if you go back in climatic science, they know that 100,000 years ago that there was a massive ice age going on, and it was super cold, and that's not healthy for mankind today, the earth being so populated. The other extreme, everything's so hot. I don't know, I think it's a couple million years ago that I didn't have a chance to research. Anyway, I'm just telling you what it was. They know that all the North Pole, all of Greenland, and all of Antarctica was melted completely. And the oceans were over 210 feet higher than they are now. Okay, so if you take that as two pieces of information, 2 million years ago, 100,000 years ago, you had the Ice Age, you can see it's cyclical. Okay, nobody's arguing that something isn't going on cyclical between possibly the sun and the earth. There being some large cycle that mankind hadn't even figured out, probably might not figure out for another 50 or 100 years. Okay, that's not the issue. I wouldn't argue with that. There is a cycle, but you don't know how we fit in the cycle. You don't know really where we are in the cycle. In other words, what I'm saying is, are we just a little bit above the normal temperature line right here? Okay, or are we just before the heat is going to peak, and it's going to cause severe, bizarre weather pattern changes, which are going to start causing massive loss of crops. If you have massive loss of crops, then obviously you're going to have massive loss of human life. I would hope that would be avoided. I value life very much. I think everybody needs to have a fair fighting chance in this life. So if you don't know where you are here, you don't know how soon the heat's going to peak, you don't know how hot it's going to get, and for how long it's going to stay hot, okay, then it's fairly reasonable to think, gee, maybe mankind needs to get really active in attacking this problem, the overheating problem, while we're also attacking the carbon dioxide problem. Okay, the carbon dioxide assists in the heat. One of the bigger problems is the heat getting into the water. That takes a whole nother thing, but I'm just gonna try to throw this out here, explain it the best I can. Okay, let's say on an average day, it doesn't matter if that day is in the middle of the winter. It doesn't matter if that day is in the middle of the summer. What matters the most is your heat gain, your net heat gain or loss over, let's say, 1 month or even 1 year. 1 year. Now they say that the oceans, if the oceans heat up at 1 or 2 degrees Fahrenheit warmer, that's a big problem, because the oceans are a heat sink. A heat sink, for instance, in the heat of the day, in the summer when it's real hot and the sun goes down, if you go out on that blacktop street and you put your hand down on that street at 1 o'clock in the morning, it still feels real warm. Okay, not super hot like it is in the middle of the day, but it's still real warm. Okay, heat sinks are things that absorb a lot of solar energy and they hold it really good. Okay, a leaf on a plant, you go out and feel the 100 degrees outside, you feel the plant, it don't feel hot at all. You feel that road, you're going to burn your hand. Or the top of your home. So the on a daily basis, let's say that the sun beats down and 1 square yard of ground, either pavement or dirt, or even grass, let's say that for during the daylight, the sunshine, that it absorbs 100 units of energy, whatever that unit would be. I'm not trying to go in detail for a long bit. Okay, then as the sun sets, it starts to cool off. And what's happening is that heat is beginning to radiate back out up through the atmosphere and back into space during the night. It radiates back out into space. Okay, so if during the day 100 units of energy are absorbed, okay, we'll put day here, and then at the night, okay, 100 units radiate back to space, okay, your net gain equals 0. That's good. That's what you want. Okay. The problem we're occurring is, if you look at maps years in 1960, you look like, when they first started taking satellite pictures of the Earth, if you look down and you would see the size of the city, they were real small. Okay. The Earth has exploded with population. You look at cities now, they're, god dang, they're gigantic. Okay? Every one of those cities has a rooftop. It has more streets. It has less green space. And all of that during the summer and the spring, summer, and fall, all those areas are absorbing that heat. Now, so the game has changed. All this stuff up here, net gain equals 0. I would say back in the 60s, there was still a good solid polar ice cap up north. Part of the 70s, your net gain was more towards 0. Now, what's going on is you have 100 in the day, okay? And then come night, okay, let's say at nighttime it rains in New York City. Let's say the whole city's blistering hot that day. And right as the sun goes down, when the roads are still baking hot, and the roofs, the pavers on the roofs of the buildings are still real hot, and people's asphalt roofs on their houses, shingles roofs are still real hot. Let's say there's a big thunderstorm. Okay, and then that thunderstorm, it rains and the water hits the roof, and then it trickles off, it goes down the gutter and out to the street where it absorbs some more heat, and then it flows out into, you know, Hudson Bay or whatever it is, Hudson River around New York City. In that case, what happened is the nighttime never got there and the heat was never allowed to radiate back out to space. What happened was the rain fell, absorbed the heat off of the pavement, the roads, and the rooftops, and transferred that heat to the water, which ran into the streams and then eventually into the river. So you had a heat gain, okay? Maybe it wasn't a whole lot, but still, that heat did not radiate away. in the space. Now the water holds it, okay? And water is a heat sink, okay? It's a fairly good heat sink. And so warmer water is mixed with colder waters, and eventually that colder water gets a little bit warmer. And the striations in lakes and rivers and the ocean, you have different layers, you know. This layer's warmer, and then that one's a little not quite as warm. The deeper you go, it gets a little colder and a little colder and colder and colder. The problem is now further down, those layers down there are getting, you know, measurably warmer than they were 5, 10, 20, 30 years ago. That's what the problem is. Those lower levels are beginning to warm up in the water, in the oceans, in the lakes, you know, in rivers, streams. And then that does have an effect on everything. I think one of the easiest things that could be done to help is to in the ocean would be to place floating platforms with vegetation planted on them, so that sunshine during the day, if you have the ocean right here, the ocean right there, you know, and you got a platform here, and it could be composed of like multiple triangles of sorts that you only need it good enough and strong enough to support a little bucket with some potting soil and some slow release fertilizer, and you know, a nice healthy plant. And of course you'd have to water it out there, so you'd have to carry some, you know, containers of water, and someone would have to be there with it and float along with it. But the idea here is every quarter, let me see, quarter mile is 1,320 feet. I'm not so sure you'd have one that big, but the idea would be to hook up as many of them as possible and prevent, so the sun, you know, light would be coming down, it would hit the plants, the sun would hit the plants. Let's draw a little plant leaf here, you know, and the plant would grow. But the thing is, that sunlight that's coming down would not strike the water and warm it. Okay, so you're kind of getting a double advantage. You're growing a plant, and you're preventing sunlight from warming the water. It's a double benefit. It's an added benefit. And in some areas where the water is getting really warm, the marine life is having a hard time adapting because it's too warm. It hurts. The fish cannot adapt to it and prosper. So, but I think one of the easiest things to do. Now, of course, there's other things you can do, like working with buildings and stuff to modify them, and roof gardens and stuff like that would absolutely help also. But floating platforms in the oceans, perhaps, I think it should be looked into. But and the other thing about rooftop gardens, I'd have to give that a later talk. But anyway, it's just something to think about. And I'm probably over my time anyway, thanks. Let me see. 19 minutes? Oh my God.